this is the um, fourth part of this series where I just try and solve the problem to determine all real numbers alpha such that the sum of the floor of alpha plus 2 alpha, floor of 2 alpha, all the way up to n alpha is a multiple of n, and that's for all n in the natural numbers. To summarize what we've got so far, we've found that if S is the set satisfying the condition above, that it contains the even integers. Doesn't contain the odd integers. And what we've done is we've split that set up in terms of S of n, where n is where we kind of fix the n that is in the problem statement. We've also found that if we have a solution, or if we have a value that's in S, then any shift of that by an integer must be in S as well. So we can, because of that, we can focus on the interval between -1 and 1, let's say, or any interval of length 2. And if we can find the alpha within that interval that are in S, then we've got all of the alpha that are in S. And yeah, last time I gave a conjecture as to what the individual Sn were. So that Sn, if n is even, Sn is the 2 is the even integers. Is this in, this interval in, shifted by the even integers, and if it's odd, then it's the interval in shifted by just the integers. Now, to prove this, I mean, it's a statement involving n, but I don't think it's not obvious how to attack it by induction. Yeah, and if we try and just prove it for a particular fixed n, then, you know, if we look at what we did for S3, we're going to be dealing with lots of different kind of cases for what the fractional part of the value alpha is. Even, you know, with S3, even there were 4 different cases we had to look at. So that seems not a great way. But what I thought we could try and do is, I'll just get another page here. What I thought we could try and do instead I'll just sort the pages of work that I've done. So keep this one. I'll just add another page here. Yeah, I think I'll get rid of this page. This is just rough work that basically shows that the situation for S3. And what we'll do is replace this with a blank bit of paper. Okay, and this we can carry on with our observations. So my claim, let alpha, so because of this thing about it being between, only focusing between -1 and 1, I was thinking we already know in that region, based on the first thing, that actually we can focus on between -0.5 and 0.5, because it has to be an S2, and we know what S2 is. So let's just look at alpha in, yeah, let's say it's in 0 to a half. And if that's the case, then there exists an n such that, so I'm just trying to sandwich it between two reciprocals of n. So the smaller one would be when n is bigger, so such that 1 over n plus 1 is less than or equal to alpha is less than n. And yes, and that's a unique n. So a unique n such that this is the case. And that n obviously has to be greater than or equal to 2. So, for example, if n is 2, then we're saying that this is between 1/3 and a half. And if not, then it's between 1/3 and a quarter. And if not, then it's between 1/4 and a fifth, and so on. We can just keep doing that. So, yeah, so let's just assume that we have that n. For that n, let's look at, for that n, fn of alpha, which is equal to plus 2 alpha plus plus I think we want fn plus 1 of alpha plus n alpha plus n plus 1 alpha. That is equal to, well, just from here, from the left hand side of this, you can see that n plus 1 alpha is greater than or equal to 1. And we know that n alpha is less than 1. And of course, alpha is positive, n is positive, so this is greater than 0. Now, we want to show that if n plus 1 alpha were greater than or equal to 2, then n alpha plus alpha is greater than or equal to 2. Okay, let's ignore this for a bit. Point with this is that for basically every value up to n plus 1, these are all zeros. And then this one is at least 1. So that's just this. Okay. Now, could it be greater than 2? So let's just ask that as a question. Could n plus 1 alpha be greater than or equal to 2? Then alpha would be greater than or equal to 2 over n plus 1, but also less than 1 over n plus 1. So 1 over n plus 1 is greater than or equal to 2 over n. So 1 over n is greater than or equal to 2 over n plus 1. So n plus 1 is greater than or equal to 2n. So 1 is greater than or equal to n, as in, so n is less than or equal to 1. And that's a contradiction. So n plus 1 alpha is actually in 1, 2. And that means that fn plus 1 of alpha is equal to 1. So, just going back to the original claim, we've shown that alpha is not in Sn plus 1 because it has to be a multiple of n. And we know that n is greater than or equal to 2. So alpha is not in Sn plus 1. So we've shown, and that of course implies that alpha is then not in S. So we've shown that for all of values, these positive values. And hopefully, I think we should be able to show something similar for the negative values. So the only things left are, between minus a half and 0. So I'm just going to summarize what we've done here. We've shown the claim. If alpha is in 0 half, then alpha is not in Sn plus 1. Now, let's clear this, and we're going to do the exact same thing again, but with minus a half to half. No, it looks very similar. Probably could do some symmetry thing. What's the relationship between the negative of the floor of the negative of something and the floor and the negative of the floor of it? I mean, it's mostly going to be symmetric except for those sort of edge cases. So I'm going to clear I'm going to create a new, yeah, I'll clear this. And we'll now say let alpha be in minus a half to 0. It's now negative. Then there exists an n such that alpha is yeah, so now we've just got to be a bit careful with these inequalities. So which is smaller, minus 1 over n, minus 1 over n plus 1, which is closer to 0. Be minus 1 over n plus 1. So that'll be over here. Since the bottom's bigger than that. And again, this is actually a unique value of n. So long as we just make one of these, so which side should be the equality. So what do we have before? Yeah, we had, so we'll do it like that. Okay. Then the left-hand side just shows us that minus 1 is less than n alpha. And we know that n alpha is less than 0 because we know that n is positive. So these are, oh yeah, we should say okay, so that's it. Should be that way around. So this should be then at least 2. So if n is 2, then that's saying that's between, the alpha's between minus a half and minus 1/3, so on. Okay, so then that says that minus 1 is less than because of that, which is, and that is greater than 0. And the right hand side then says that n plus 1 of alpha is less than minus 1. Once again, if n plus 1 alpha were less than minus 2, then alpha is less than minus 2 over n plus 1. But it's also greater than or equal to minus 1 over n. So 1 over n is then greater than 2 over n plus 1. And this is the same as before, so n plus 1 is then greater than 2n, and 1 is then greater than n, which is a contradiction. So we've got the n plus 1 alpha is then in the interval minus 2 less than minus 1. Yeah, so it's in that interval. Okay, so therefore f of n plus 1 of alpha, which is this, well, everything up to n alpha is less than 1. So the floor of that okay, something slightly different here. So we've got the floor of these. Then they actually become, that's minus 1 a load of times. Let's see if this still works, but may not work. So this is minus 1 n times, so minus n. And then this then is, so the floor of that then is minus 2, which is minus n plus 1 minus 1. So is that divisible by n plus 1? Well, no. So, yeah, okay. So we're lucky. Really, I didn't plan for that. N, that's minus n. That's minus, yep. So alpha is then not in S, F, n plus 1. So alpha is not in S. Okay, so going back to, so we'll just store that here. Another claim, which we've proven, is if alpha is in this interval, then alpha is not in Sn plus 1 as well. So now we've shown really so altogether we have shown that S is equal to 2z. And that's it. So I think what I'll do next time is I'll probably just go through and check that and then try and write up our argument. But I think we've got the result. Let's go back to the original. Yeah. Yeah. Stop the video here, and yeah, so next time we'll just gather together that and just try and write up the proof.